Okay, today guys we are going to talk about continuity and think about what that means in the most basic sense. That means you can trace it without picking up your pencil. The formal mathematical definition gets a little more complicated looking, but if you ever get confused and you're asking yourself the question, is it continuous? Ask yourself if you can trace it without picking up your pencil, and if so, it is continuous. Now, a lot of people say continuous and discrete are opposites, and they very much are. Continuous, something that's smooth, you can trace it without picking up your pencil, no problems, no holes, no jumps, nothing. Discrete, the true meaning of discrete, as far as functions and data go, mean something more like a scatter plot. It passes the vertical line test, but it's all everywhere. It's points individual, not connected. Most graphs that we work with are either continuous or partially continuous and have some problems. Occasionally we work with data sets that are discrete, but we really don't get into a lot of information with those in this class. So we're going to stick to continuous and some things that are partially continuous. So I need to talk about some of the problems that we face. Okay, there are four main problems that we run across when we are talking about things that have issues with continuity. And so I'm calling these the types of discontinuities. The first is a point discontinuity. It's also known as a removable discontinuity because you can write a piecewise function and fix the problem. But a point discontinuity is when your function's going along, it's continuous, but then it has a hole all of a sudden. And so there's a hole in the graph, and we know how to find those algebraically from previous units. Jump discontinuities are ones where the graph literally jumps. So it might be coming along and all of a sudden jump up to another point, another y value, totally skipping the y values in between. It would still have to pass the vertical line test. So my little example here, I have an open circle here and a closed circle here so that we would pass the vertical line test. Infinite discontinuity would be when you have an asymptote. So if I have an asymptote, let's say a vertical asymptote coming down through here, and I have, the graph coming along, it hits the asymptote and doesn't have an x value on the asymptote, and then it's coming along and still affected by the asymptote on both sides. So that's infinite discontinuity. Again, think of asymptotes when you think of that. The last one is really weird, and the best case I can give you to graph is y equals sine of 1 over x. If you'll graph that in your calculator, you'll see something like that almost resembles a sine graph, but as it gets close to 0, it starts oscillating back and forth so much, and you can't really pin down a y value that it's close to. If you zoom in, it will get even more and more back and forth going. It's a very strange function, but you only see it once in a while. That is oscillating discontinuity. It's considered discontinuous at that point. Okay, before we move on to some actual examples and problems, I want you to put a big fat star in your notes. And I want you to think about a function that has a hole. The thing that people seem to get mixed up on is limits and continuity. When your graph has a hole, the limit exists. So the limit does exist. Why? Because the left side and the right side are both going to the same y value. The point's not there, but they're approaching that same y value, and a limit means approaching that y value. The point is considered discontinuous. It is not continuous because the point is not there, and you'd have to pick your pencil up to go over it. So the limit does exist, but it is not continuous. This is the main thing that people get confused. Please make every effort to keep those two things straight. Okay, this is a typical problem, our first example here. So find A so that f of x is continuous, and they give us f of x equals this piecewise function, 2x minus 5, and ax squared meeting at 2. And so what you do is, because it has to be continuous, that means their outputs have to be the same. You plug the place where they meet into both equations. So 2 times 2 minus 5 would be plugging it into the top. And you set them equal. Make sure you're plugging in for x because it's meeting at an x value. So a times 2 squared. Then here, if I work this out, I get a negative 1. And I have 4a. And if I divide, I get a to be negative 1/4. So again, all I've done is take the x value where they meet, plug it into both sides, and set them equal to each other. That should create an equation that you can solve. Okay, so here's another example. If you want to try it your own way, then pause and see if you can. If not, again, I'm finding m so that g is continuous, so they're meeting at negative 3. I'm going to plug negative 3 in for the x in both equations and set them equal. So m times negative 3 plus 4 is going to equal negative 3 squared minus 11. So over here, I'm going to have negative 3m plus 4. On this side, I'm going to have 9 minus 11, which is negative 2. And if I subtract 4, I get negative 6, divide by negative 3, and I'm going to get m to be 2. Okay, for our next example, they're asking us to classify the discontinuities. And classify means give it a name. So we're going back to those 4 things, point, jump, infinite, and oscillating, to figure out what's going on here. You have to also remember from our rational unit what these things mean. Because I want to cancel out the x minus 1s, I know I have a hole at 1. In our language here, that is a point discontinuity. So point discontinuity at x equals 1. I also have, since that's a hole, don't think about it, I also am going to have a vertical asymptote at 3, because that will be giving me a 0 on the bottom. And a vertical asymptote is an infinite discontinuity. So infinite discontinuity at x equals 3. The 0 at negative 2 is not a discontinuity. It just means it crosses the x-axis. So that's not a problem. Okay, for example 4, I have a piecewise function. And whenever they're asking about discontinuities, the first thing I do is check to see if I have any holes or asymptotes in the actual equations that they're giving me to put together. And since I don't, because an x squared's continuous and an x plus 3 is a line, so it's continuous, I'm going to go ahead and check the place where they meet. So if they meet at the same place, it should be continuous, and if they meet at 2 different y values, they're not actually meeting, and therefore it's a jump. So I'm going to do the similar thing to what I did with the limits, and I'm going to plug in. 2 times 1 squared minus 1 is going to give me 1. And then 1 plus 3 is going to give me 4. And they don't meet at the same place, so that means there's a jump. So I would answer there is a jump discontinuity at x equals 1. Okay, for example 5, again, I start by looking at the pieces of the f of x to see if they have any problems. And again, these are all continuous toolbox function shifts with no problems. So I come over here and I see about where they meet. Well, everything is meeting at 1. This is the left side, this is the right side, and this is the point. So everything here needs to have the same output. When you're doing limits, you can ignore the point and just do the left and the right sides. But when you're doing continuity, everything needs to be the same. And so if I plug in 1 to the top, I get, hang on, let me change color for you so you know it's my work. If I plug in 1 to the top, I get 1 squared plus 3, which is 4. If I plug in 1 to the bottom, I get 1 plus 3, which is also 4. But plugging into the middle, I get 2 because it's a horizontal line. And what that means is that the left and the right sides are going to 4, but the point is actually at 2. So this is a point discontinuity. At x equals 1. Okay, for our last example, I have kind of a weird function here. It's also piecewise. But if you look where they meet, it's not like left and right like it has been. We have x not equal to 0 and x equal to 0. What that means is it looks like a parabola everywhere but 0. So here's your parabola, except I'll have to do it as I go, I guess. Except at 0 you have a hole. So it looks like this parabola everywhere but 0. And then what this is saying is at 0 it's at 3. Well, normally on a parabola we're at 0, 0. So this means I have a point up here. And so if you think about what that graph is meaning, you can tell that it is a point discontinuity at x equals 0, because the sides are there, but you would have to jump over it to be able to trace that. So it's discontinuous at that point. This concludes the continuity video.